Hello everyone, welcome back to this online class. Today we are going to look at numerical integration, and in particular we are going to look at Simpson's 3/8 rule. Now we have this question. We are asked to discuss Simpson's 3/8 rule and hence work out the following question. In number one, we are given that a tank is discharging water through an orifice at a depth of x meters below the surface of the water, whose area is a square meters. The following are the values of x for the corresponding values of a. So we have the table of a versus x values. Using the formula 0.018 t is equals to the integral from 1.5 to 2.85 of a over root x dx. Calculate the value of t. That is the time in seconds for the level of water to drop from 2.85 meters to 1.50 meters above the orifice. Using Simpson's 3/8 rule, correct to 3 decimal places. Hence, obtain a bound for the truncation error. So let's see first of all how to derive Simpson's 3/8 rule. So when I talk of discussing, we are going to derive the rule and also derive the formula for the truncation error bound. So let me take you down here. I want us to take a note that f of x must be a continuous function, must be continuous. And remember, the task is to evaluate the integral from a to b of f of x dx. That's the problem. We need to find the area enclosed by the curve y is equals to f of x, the x-axis, and the lines x is equals to a and x is equals to b. So let me sketch the region that we are interested in. So we'll have here x versus y. This is x, this is y. Let's say our region is something like this, something like that, so that at this point we have a, at this point we have b. We need the area enclosed by the curve y is equals to f of x, the x-axis, which as the equation of y is equals to 0, the lines x is a and x is b. So typically it's this region. That's what you mean by the integral from a to b of f of x dx. So now you see, we are simply approximating that area. So in this case, we are going to be approximating the area using Simpson's 3/8 rule. So there are two steps that we need to follow. The first step, step 1, is to divide the interval. Divide the interval that is from a to b into n subintervals. Of course, we require that n must be divisible by 3. N subintervals of course you write where n is divisible by 3. By 3. So subintervals of equal width h, equal width h. H is given by b minus a over n. So what are the subintervals? The subintervals are from x naught. Let me first of all divide so that we see what's going on. So when I say, remember, when we have a, that is the same as x naught, and when we have b, is the same as x n. So we are subdividing into very, very thin strips. Remember, we are going to be picking 3 strips at a time. Again, you subdivide 1, 2, 3. So there are so many of them up to the last ones. Those are straight lines, remember? 2, 3. So this is x1, x2, x3, x4, x5, x6. Here will be xn minus 1. This is xn minus 2. This will be xn minus 3. Remember, there are so many other x values in between. So our subintervals are from x0 to x3. We are picking 3 at a time. So the first 3 strips, that is from here all the way up to here, so that you approximate the integral in this region. The first 3 strips from x0 to x3. Another one is from x3 to x6. x3 to x6. So again, we pick these other 3 strips. And lastly, we'll have xn minus 3 to xn. So there are so many of them, of those intervals. Then xn minus 3 to xn. So the next step is to fit an interpolating polynomial. So you can write here step 2. You write fit Newton's forward difference interpolating polynomial of degree 3 on each of the n over 3 subintervals. Each of the n over 3 subintervals in general is given by xi to xi plus 3. And in this case, I ranges from 0, 3, 6, etc. So you can write for I is equals to 0, go to 3, go to 6, go to 9, all the way up to n minus 3. So why are we fitting a polynomial of degree 3? This is the illustration. If you look at any 3 consecutive strips, let's say this is point A, here we have point B, here we have C, and here we have D. Those are ordinates, yes, but now they are ordinates corresponding to the first 3 strips. So those are 4 points. When you have a table of data with 4 points, then it means that your interpolating polynomial must be of degree at most 3. And that's why we insist on using the Newton forward difference interpolating polynomial of degree 3. Again, from D, let's say here we have E going to F, going to G. Again, the next 3 strips is from D all the way up to G. Of course, 4 ordinates, 3 strips. Now, again, those are 4 points. It means you can come up with an interpolating polynomial of degree at most 3. So I have explained why we have to use an interpolating polynomial of degree 3. Now, what is this polynomial? Let me write it in explicit form. Before I write the polynomial, let me explain why it is of degree 3. So you can write since one can obtain only, since one can obtain only third order differences from any 4 consecutive points. So the polynomial now will be where there is f of x, we will approximate this by fi plus s delta fi plus s minus 1 over 2 factorial, second order forward difference of fi plus s minus 1, s minus 2 over 3 factorial, the third order forward difference of fi. That's our interpolating polynomial of degree 3. So therefore, if you want to calculate the integral, simply evaluate that integral. So you can just say that now, to evaluate the integral from a to b of f of x dx is the same as writing the integral from x0 to x3. Remember, we are picking 3 strips at a time of f of x dx plus the integral from x3 to x6 f of x dx. There are so many of them up to the last 3 strips, which is from xn minus 3 to xn of f of x dx. And so in terms of summation, it's the same as writing the sum from I is equals to 0 to n minus 3 of the integral from xi to xi plus 3 of f of x dx. And so I'll bracket this. So I need to work out the integral that is inside that summation. Once I know its value, then I'll now take the sum from I0 all the way up to n minus 3. So you can write for I is equals to 0. You go in steps of 3, 3, 6, etc. up to n minus 3. It must be in steps of 3, 3, 3. So let's now work out the integral that is inside that summation. So you can say here that now the integral from xi to xi plus 3 of f of x dx is approximately equal to, now I'm going to use the polynomial that is Newton forward difference interpolating polynomial of degree 3. And so because that polynomial depends, it's a function of s, that means we need to define a transformation. Our transformation is this one, that we let s be equal to x minus xi over h. So this simply means that if I make x the subject, this means that x is the same as xi plus sh. So what about if I differentiate dx ds? What will it give us? So from here, you get dx is equals to h ds. Now, what about the limits of integration? Limits of integration. When x is equals to xi, it means our s will be equal to xi minus xi over h, that is 0 over h, which is 0. And when x is equals to xi plus 3, it means that our s will be xi plus 3 minus xi over h. Remember, if I have this, let's say xi is here, then followed by xi plus 1, then xi plus 2, then xi plus 3. The spacing between them is h, and the step size. So when I want xi plus 3 minus xi, that is simply 3h. So that is 3h over h, which is simply 3. So we are now going to be integrating from 0 to 3 of the new interpolating polynomial of degree 3. So let me replace everything. So this is the same as approximately equal to the integral from now s is equals to 0 to 3. Our polynomial is fi plus s delta fi plus s minus 1 over 2 factorial delta squared fi plus s minus 1 s minus 2 over 3 factorial delta cubed fi. Also replace dx. Dx the same as h ds. So h is a constant, I can factor it out. Let me write here ds, and you can write h outside. Wrap this so that I write h outside. So that's approximately equal to h times that integral. Now let's work out the integral. So this integral will now give us h, then here we'll have s fi plus s squared over 2 delta fi plus, remember this is the same as 1 over 2 factorial times, this is s squared minus s. When you integrate, you get s cubed over 3 minus s squared over 2 delta squared fi, then plus 1 over 3 factorial. When you integrate this, let me expand this. Here, we'll have s, of course, s into, what is this? S minus 1 times s minus 2. That is s squared minus 3s plus 2. Then times s, that will give us s cubed minus 3s squared plus 2s. So when I integrate that, you get s raised to 4 over 4 minus s cubed plus s squared delta cubed fi. And so this is from 0 to 3. S is equals to 0 to 3. That's what we have. So let us plug in the limits of integration. What are we going to get? When you substitute the limits, we are going to get h We are starting with 3, so that's 3fi. 3 squared, that's 9. 9 over 2 delta fi plus is the same as 1 over 2 times 3 cubed is 27 over 3, that's 9. So 9 minus 9 over 2. That will give us 9 over 2 delta squared fi plus 3 factorial is 6. So that's 1 over 6 times 3 raised to 4. That is 81. You divide by 4. Then subtract 3 cubed, which is 27, plus 3 squared. So press that in your calculator. So that should give us 9 over 4. 9 over 4. Then there's delta cubed fi. Remember, when s is 0, the result will be 0. So I don't need to work out when it is 0. So now I'm going to replace this forward difference operators, the first order, second, and even the third order. So write a note here that we know that forward difference of fi is the same as fi plus 1 minus fi. The second order forward difference of fi is the same as, we can derive it, is the same as forward difference of another forward difference of fi. And so that is forward difference of fi plus 1 minus fi, which you can write as forward difference of fi plus 1 minus forward difference of fi. And so this is the same as fi plus 2 minus fi plus 1, then minus fi plus 1 minus fi. When you simplify, you get fi plus 2 minus 2 fi plus 1 plus fi. Also, we need third order for a difference. So let's also work out that. Third order for a difference of fi is the same as forward difference of now the second order forward difference of fi, which we already found. So it is forward difference of fi plus 2 minus 2 fi plus 1 plus fi. When you break it down, it will be forward of fi plus 2 minus 2 times the forward of fi plus 1 plus the forward difference of fi. Work out each of them. The first term will give us fi plus 3 minus fi plus 2. The next term is negative 2. This is fi plus 2 minus fi plus 1. And the last one is fi plus 1 minus fi. So fi plus 1, then minus, remember this is 1, minus fi. So when you simplify, you get fi plus 3 minus 3 fi plus 2 plus 3 fi plus 1 then minus fi. That's what we'll substitute now here. So let's replace those functional values in this integral so that our integral will now be equal to h 3fi Then plus 9 over 2, fi plus 1 minus fi plus, so replace everything in that whatever we have on the right hand side. So this is what we get. Now I want us to simplify. As you can see, we have so many like terms inside the bracket. What I'm going to do is to factor out the 3 over 8 so that we see what we remain with. So what I'm going to do now is to factor out 3 over 8. Let's see what we are going to get. So that will be equal to, of course, now it is 3h over 8. What do we have inside the bracket? So that will be 8fi. Remember, I've factored out 3 over 8. Then the other one will be 3 over 16. Is it 3 over 16? No. That is simply, just press and see what you're going to get. It's not 3 over 16. So let me rub this one. Remember, when you factor out 3 over 8 is the same as writing this one. Let me explain. It is 3 over 8 inside. So here you have to multiply by 8 over 3. Each of them you multiply by 8 over 3. So that we'll have 3 times 4, which is 12. So I'll have here 12 times fi plus 1 minus fi. So let me rub the 8 over 3. And by each of them, you're multiplying by 8 over 3. So here I'll have 12 into fi plus 1 minus fi. Again, the other one, 9 over 4 times 8 over 3. So that will be, let me write here 8 over 3. I'll check here 2, 3, that will be 6. So that will be 6. Then here we'll have fi plus 2 minus 2 fi plus 1 plus fi. 3 over 8 times 8 over 3, that is 1. So here we'll have plus fi plus 3 minus 3 fi plus 2 plus 3 fi plus 1 minus fi. So that's what we have. Now look at 8 fi times, of course, there's another minus fi. I want to combine the like terms, that's what I mean. 8 minus 1, that is 7. Another fi is minus 12. So you press 7 minus 12, that will give us, press that and see what you're going to get. So that's negative 5. Then there's another fi here, which is 6 fi. So negative 5 plus 6, that is positive 1. So that's simply 1 fi. So what I write here, this will be equal to 3h over 8. In now bracket, now we remain with 1 fi after combining all those fi's. Let's see the fi plus 1. What will we get when we combine them? So we'll have here 12 fi plus 1 minus 12. So that will cancel. So that is 0. Then I can see there's another one, 3 fi plus 1. So I have here plus 3 fi plus 1. Let's get to fi plus 2. I have here 6. Another one is negative 3. So again, that is 3 fi plus 2. Followed by, this is 3. That should be 3 fi plus 2. Now we have fi plus 3, which is just 1. So plus fi plus 3. When you simplify, that is what you need to get. So we can as well write this as, because I can see the 3 is common, so I can factor that 3, so that this can as well be written as 3 over 8 h into fi plus 3 into fi plus 1 plus fi plus 2. fi plus 2, then plus fi plus 3. That's what we have. On the left, it was the integral from xi to xi plus 3. So you can just write the integral from xi to xi plus 3 of f of x dx is approximately equal to, it should be an approximate, so you can say is approximately equal to that. Remember, that's not the exact. So this is very important. So now when we take it back to our summation, that is from I is equals to 0 to n minus 3, what are we going to get finally? So you can write that if you substitute that value back to this equation, let's call this equation star. So you can say hence equation star becomes, substitute that back to equation star. So when you substitute the values of I, this is what you get. Remember, I've replaced when I is 0 to give me this first bracket. When I is 3, the second bracket. So many of them up to when I is n minus 3. So that you can see there's 3 over 8h is common. That can be factored out. So you can write here 3 over 8h. Let's combine f naught, it only appears once, plus those that appear 2 times. Which ones are they? You can check. So you can simplify and then write what you get finally. There are those that appear 2 times, there are those that appear 3 times. So when you simplify this, what you need to get, that integral is the same as 3h over 8 f naught plus twice f3, f6 plus all the way up to fn minus 3, n plus 3 times f1, f2, f4, f5 plus so many other terms up to fn minus 2 plus fn minus 1, and then plus fn. So in other words, it is the same. This is the Simpson's 3 over 8 rule. So let me just bracket this one. So you can just say the integral from a to b of f of x dx. I can bracket it and comment that this is the Simpson's 3 over 8 rule. Comment on this. Simpson's 3 over 8 rule. So in words, what does it mean? In words, it is the same as 3h over 8. Then here we have the sum of end ordinates that is the f naught that you can see here and fn. Those are the end ordinates. Then we have plus twice sum of the ordinates, whose subscripts, you can write sum of middle ordinates, middle ordinates whose subscripts are divisible by 3. As you can see, F3, 3 is divisible by 3. F6, 6 is divisible by 3, all the way up to Fn minus 3. N minus 3 is divisible by 3 because n is also divisible by 3. And then plus 3, the sum of middle ordinates whose subscripts are not divisible by 3. Not divisible by 3. So that's the Simpson's 3/8 rule in words. Now, the truncation error bound in using this rule is given by, of course, you can follow our derivation in Simpson's third rule, and also in Simpson's, not Simpson's, but trapezoidal rule. So this is how you need to get your truncation error bound. So you can write here that the accuracy or truncation error bound, let me use red. So we all know that to get the error, you need to take the exact value of the integral, then minus the approximate value of the integral. So first of all, let's see how to get the exact value. Remember, our integral is this one. It is the integral from xi to xi plus 3 of f of x dx. So what I'm going to do, I'm going to expand f of x in Taylor series about xi. So you write expand f of x in Taylor series about xi. Remember the Taylor series expansion that f of x is the same as the sum from n0 to infinity, n0 to infinity of the nth derivative of the function. So nth derivative denoted this way of the function at xi over n factorial, then times x minus xi. This is raised to n. That's the Taylor series. So when you open up the summation, you're going to get this. So it is now the integral from xi to xi plus 3. The expansion for that is f of xi, that is fi, plus the first derivative, then times x minus xi, plus the second derivative over 2 factorial. Remember, that is fi. So you can go all the way up to the fourth order term. Now for us to be able to evaluate this integral, we need to make t substitution. We are going to say let t be equal to x minus xi so that we can simplify the problem. So you can write here, let t be equal to x minus xi. So now I'm going to convert everything in terms of t. Even the dx will change. So when I differentiate, I'm going to get dt is equals to dx. What about the limits? When x is xi, the lower limit, what will happen to t? T will be 0. What about when you put x is equals to xi plus 3? That will give us 3h. So this will give us t is equals to 0, and this will give us 3h. So you can write when x is equals to xi, it is clear that t will be xi minus xi, that is 0. And when x is equals to xi plus 3, you see we'll now be having xi plus 3 minus xi, which we said is the same as 3h. Already we had illustrated that, so let's substitute into our integral. What are we going to get? Replace everything, even the limits and even the x. Now, when you replace the x minus xi in terms of t, now you are going to get fi plus fi prime t plus fi double prime over 2 factorial t squared plus fi third prime over 3 factorial t cubed, and then fi fourth derivative over 4 factorial t raised to 4 plus so many other terms. Now integrate with respect to t from t is equals to 0 to t is equals to 3h. So that when you integrate, you're going to get this. The first time, remember these fi's are constant. So with respect to t, we are going to get t times fi. That is t times fi. Plus the other one is t squared over 2. T squared over 2. 2 factorial just, this is t squared over 2. When you integrate t, then here we have fi prime. The other one, t squared will give us t cubed over 3. 3 times 2 factorial, that is 6. So that is just t cubed over 6 fi double prime. Proceed with the other terms up to the last one. Now you need to substitute or simply plug in the limits of integration. That is from 0 to 3h. These are the limits for t. I'll start with the upper limit. When t is equals to 3h, what will you get? And also when t is 0. Of course, when t is equals to 0, you are going to get 0. So let's just use 3h. When t is equals to 3h, we are going to get 3h fi 3h squared, that is 9h squared over 2. So this is plus 9h squared over 2 fi prime plus, so work out the remaining terms. Where there is t, you put 3h. So when you work it out, this is what we need to get as our exact value of that integral. Now, what about the approximate value of the integral? We already got it. So you can write here approximate value. Remember the same integral. And let me take you back to where we got the approximate value. It's somewhere here. When you are deriving the formula, look at the approximate value. It is this. So this is what we have as the approximate value. But now what you're going to do, because if you look at the exact value, all the subscripts are i's. But here we have I plus 1, I plus 2, I plus 3. So what I'm going to do is to expand I plus 1, I plus 2, and fi plus 3 in terms of fi. That means you expand about xi, expand in Taylor series. So let me write this down. It was 3h over 8 fi plus 3, fi plus 1 plus fi plus 2, then plus fi plus 3. I'm going to write it down. Xi to xi plus 3 of f of x. So now this is what you need to expand. Let's start with the fi plus 1. F subscript I plus 1. How else can you write this? is the same as writing f of xi plus 1. Xi plus 1. And remember, xi plus 1 is the same as xi plus h. So it's the same as f of x, I, then plus h. So when you go to the Taylor series expansion, where there is x, you replace that by xi plus h here. We now replace this by xi plus h. Even here, you replace also this with the xi, then add to h. So you see that will now be a series in powers of h, because the xi will cancel with this other xi. This and this will cancel. So what you remain with now is a series in powers of h. So that that series can now be written as, so let me take you down. When I expand it, this is what I need to get. So we have expanded fi plus 1. We get what we have written in black. But let's also expand fi plus 2, which is the same as f of xi plus 2. Remember, xi plus 2 is the same as xi plus 2h. So when you go to the Taylor series expansion, where there is x, I'm going now to substitute xi plus 2h. So now it is 2h. Here again, it is 2h. So it will be a series in powers of 2h. That is not h, but 2h. So when you expand, this is what you need to get for the fi plus 2. And you do the same to fi plus 3. So when you expand fi plus 3, you need to get this. Now let's substitute them back into this equation. So that is 3h over 8. Then you take fi plus 3, replace the value you got here and also the value you got here and the value you got here. So when you substitute and you simplify, this is what you need to get. So you can just say that therefore, remember we are substituting back xi to xi plus 3 of f of x dx. That will give you, if I combine the fi's, remember here we have 3h over 8, so that combine them. This you take here, so we'll have fi plus another fi, that is 2, 3, 4. So that will be 4fi, then times 3h over 8. So what will it give us? That will give us 3h fi. So you write the result down here. And remember something that I've not explained here. It is fi. When we get to this is now 3 times the whole of fi plus 1. So we have fi plus 3, that is now 4 plus another 3 here. That is 7. Then plus this other one is 8. Or alternatively, just substitute everything and then open the bracket. You will see how those terms are cancelling out. So upon simplification, this is what we need to get as our approximate value of the integral. So let me call the exact value. Let me call this A, equation A. That was the exact value of the integral. And now the approximate value, let us call it B. So when you want to find the error, it is simply A minus B. And if you look at them, when you subtract, you see the first terms are the same all the way up to the third order term. The only difference arises when we have the fourth order term. Here it is 81 over 40. Here we have 33 over 16. So all these terms will cancel up to the third order term, except the fourth order term. So that this is now our error. So you can say that the error is equals to part A minus part B. The answer in A minus the answer in B. So the error we denote by E subscript I. So when you subtract, it will give us, of course, I'll have 81 over 40 minus 33 over 16. Then there's h raised to 5, the fourth order derivative at xi. Then there are so many other terms. So when you work out this should be able to give you negative 3 over 80. So write it down, negative 3 over 80, h raised to 5 times the fi, the fourth order derivative, plus so many other terms. So what we do here is to truncate the series up to the fourth order term. So we neglect the other terms which are missing from there, so that we say that after you have truncated that series, okay, just write truncate. After the fourth order term to get, I would write so many things. So once you truncate, this is what you need to get. E subscript I is now approximately equal to negative 3 over 80 h raised to 5, then times the fourth order derivative at xi. But I said we are only interested in the absolute error, so take absolute on both sides. Absolute on both sides here. So what will it give us? It will give us 3 over 3 h raised to 5 over 80. Then the absolute of the fourth order derivative, that one. But you see, we need the total error. Total error now, you sum them from I0, because we said here, let me comment. Remember, I ranges from 0, then you go to 3. After 3, we go to 6, etc. Then the last value of I should be n minus 3. So we'll have here n minus 3. So that when you want to get the total error is now, the total absolute error is now the sum of all those errors. So you write E0 when I is 0 plus when I is 3, that will give us E3 plus when I is 6, that will give us E6. There's so many of them, but remember it is in steps of 3, 3. Don't confuse it. Plus, there's so many of them in between, up to the last one, when I is n minus 3. So this is approximately equal to, now replace the values in each case. It is 3h raised to 5 over 80. Then those fi, the fourth derivative. Let's replace them. So this is what we need to get. Now, how many of these do we have? There are n over 3 of them, because you see we are writing them in steps of 3. So these terms are n over 3 terms. And now we can say that this should be less or equal to 3h raised to 5 over 80 times, I said there are n over 3 of those terms, because you see we have left so many other terms. We have left when I is 1 and when I is 2. We've also jumped when I is 4 and 5, etc. That's why they are n over 3 terms only. They're not n terms, but n over 3. Then times the maximum. I just want the maximum of those terms between a x less than a less or equal to b of the absolute of f, the fourth derivative of that function. So if you work out, you see 3 will cancel with 3. So this can as well be written as, and remember that h is the same as b minus a over n over n, so that where we have h raised to 5, that can be written as h times h raised to 4. So this can as well be written as h over 8 times, of course, this n there, times h raised to 4 times the maximum between a less or equal to x less or equal to b. Here we have f, the fourth derivative of that function, f of x. So what is h times n? H times n is the same as b minus a. So that's what I'll write in place of h minus times n, so that this one here is b minus a. B minus a. So therefore, to get the truncation error bound when using Simpson's third rule, it should be not a third, Simpson's 3 over 8 rule, it should be less or equal to b minus a over 8 h raised to 4 times the maximum between a less or equal to x less or equal to b. So that's how to find the truncation error bound in this method. Let me bracket it. Now we have seen how to derive the formula for the Simpson's 3 over 8 rule and how to get the truncation. Of course, I've left out something very important. It's a maximum of, I've left out the absolute f prime, the fourth derivative of the function f of x. So that's what I left. So this is how to get the truncation error bound when you use this formula. Now let's see how to work out the equations. You can work out the equations. So let me take you up to where we have the equation. So this is the equation. Let me just explain what you need to do here, because now you have the formulas. What you're going to do here is, you see, our task is to, first of all, evaluate this integral. That's the integral we need to approximate using Simpson's 3 over 8 rule. So our a is 1.5, our b is 2.85. Our f of x is a over root x. Remember, f of x in this case should be equal to a over root x. A over root x. But if you look at the table, we are not given a over root x. So we need to come up with another row where we have f of x. So introduce another row here where we'll have f of x. So you take the a values, then you divide by the root of x. So for instance, we can pick our a is 1 point. The first column is 1.257. We are dividing by the root of 1.5, square root of 1.5. What do we get? We get 1.0263. That's what I write here, 1.0263. You can round up to 4 dp. So proceed to fill all those values of f of x up to when x is 2.85. So once you have that, go straight away to the formula for the Simpson's 3/8 rule. Get the value of this integral and make t the subject. Once you have your value, remember we need to calculate t. So we are going to make t the subject to divide through by 0.018. That will give you the approximate value of the integral, as simple as it is. And of course, here you have been given the table. It's just populating the values of f of x, so that here we'll have f0, f1. Here we have f1, the value there, f2, f3, f4, f5, f6, f7, f8, f9. So we go all the way up to f9. So how will the formula look like? It will be 3h over 8. Remember, in words, it is f0 plus fn. Fn will be somewhere here. The end ordinates. And in this case, our last is 9. The last one is f9. Then we now remain with between f1 to f8. So 2 times those whose subscripts are divisible by 3. So that would be f3 plus the next is f6. Do we have another one between 1 and 8? No. Then the rest you multiply them by 3. The rest from f1, the remaining 3 times f1 plus f2. I cannot write f3 because already we have it. So we go to f4, f5, f4 plus f5 plus f6 already is there. So we go to f7, which is missing, and then f8. I said these other ones that we multiply by 3 are those whose subscripts are not divisible by 3. So this is how you are going to use your Simpson 3/8 rule to get your answer. And somebody might be asking, how do we get h? H is the spacing between the x values. So just subtract between 1.5 and 1.65. What is the interval? Between 1.65 and 1.8. What is the interval? So you'll find that h is uniform in that case. So that will give you h. And now, lastly, we need to obtain a bound for the truncation error. Now you have the formula. All you are going to do is to differentiate f of x 4 times. Remember, a is a constant. Differentiate this 4 times so that you get the fourth derivative of that function. Then get the maximum between the interval. Our interval is between 1.5, that is a, and 2.85, that is b. Get the maximum of that fourth order derivative, and then substitute that into the formula for the truncation error bound. Let me take you back to the formula for the truncation error bound. So you are going to substitute them here. You know the value of a, you know the value of b, you know h. And so here, the maximum you can get it, because we have said our f of x here is a over root x. So you can be able to work out and get the maximum in the interval a, b. So remember, I've not done this question. I've just explained what you need to do because I know you can do it. What was very important is knowing how to derive the formula for the Simpson's 3/8 rule and the truncation error bound. So do that and compare your answers. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we'll look at more problems involving numerical integration. Bye-bye.